Hi folks, this is lesson 4 I think from the radiation topic P4 and this one's about half-life. So I want you to be able to describe how to measure the half-life of radioactive sources. There's a little cartoon on the front here and it's all regarding nuclear power. And I just want you to read through each one of these. I'll read them out for you in a second. And I want you to think, do any of these kind of ring true with you? Have you got an opinion on nuclear power? I'm not expecting you to know everything about nuclear power straight off the bat, but you probably do know some things about it already. You've heard it in the news or whatever. So the opinions on the cartoon are: nuclear radiation helps our planet by producing less pollution. This one says nuclear radiation is really dangerous. Its power and consequences are uncontrollable. This one says the large half-lives mean that it could be radioactive for thousands of years. This one says it's a quick and easy way to produce energy, so why not? And this one, there's just a question mark, as in, have you got your own opinion that either differs with these, disagrees with these, or do you agree with some of these, or what's your thought on it, basically? So what we're going to do is just have a think about that, and whichever Google Classroom this has been uploaded to, just pop a comment in there. Just what do you think about it? You can pause it if you want and just have a think about it. What do you think about nuclear power? Good, bad, why? What's your reasoning for? Okay, so we're going to do that in another lesson. We'll go through the pros and cons of nuclear power. So I just want you thinking about that before that lesson comes up. Okay, let's jump straight into it then. So when radioactive sources give out radiation, they decay. So in the previous couple of lessons, we've talked about radioactive decay and the idea that you have something that's unstable, a nucleus that's unstable, and to try and become stable, it gets rid of some of its excess energy, and it does that in one of three ways. Now, if you think about all the diagrams that I've shown you pictures of individual nuclei and the idea that, oh, it's decayed, it's given out energy, and it's become something slightly more stable. So last lesson, we looked at a decay chain for, I think it was thorium, and we talked about one nuclei, and then that nuclei changes into something else, and then that nuclei changes into something else. But in reality, we're not talking about individual nuclei. We're talking about, you've probably got a sample of a substance that contains millions of radioactive nuclei, and we need to discuss basically what happens with those. So imagine I gave you a lump of, let's say, uranium. That's a common one that we're going to be talking about quite a lot. I gave you a lump of uranium and it contained, I don't know, 1 million radioactive nuclei. Over time, the number of those radioactive nuclei decreases. Okay, so as it gives out that excess energy in the form of alpha, beta, or gamma, it'll become stable, it'll change into different substances, and eventually all of the radioactive or unstable nuclei in that substance will end up being stable. It also means that the substance won't be uranium anymore. Eventually it'll all convert into something else that is stable. Okay, so over time the number of unstable nuclei decreases. So that thing that started off being incredibly unstable and incredibly radioactive will eventually one day turn into something that isn't radioactive and is stable. And we need to discuss the finer points of that. This little animation on the screen that you can see there is a process called fission, and that's again in a lesson that's coming up. And the idea is that that nucleus there, right in the middle, looks quite stable to start off with, and then it absorbs a neutron and splits up. So the absorption of a neutron increases its mass a little bit, gives it a bit more energy, it becomes unstable, breaks apart. So we'll do that in another lesson, but it's pretty interesting. That's called fission. Okay, so the time it takes for half of the number of radioactive nuclei to decay is called the half-life. So I told you a second ago, but I imagine you've got a lump of substance, let's say uranium again, and it's full of radioactive nuclei. Then if you was to sit there and count, not that I'm suggesting you should do this, but if you was to sit there and count how many radioactive nuclei there were, and let's say there was 1 million, and then you timed how long it took to get to 500,000, as in half the amount, you'd have something called the half-life, and it's just the unit for half-life is time, essentially. So for example, if a lump of uranium contained 1,000 radioactive nuclei and had a half-life of 1 year, let's have a look at what would happen over the years. So 1 year later, you'd have 500 radioactive nuclei left, because its half-life has gone, as in one half-life has passed the amount of time that one half-life is classed as for this substance, and in that amount of time, because it is half-life, half of the radioactive nuclei that you started with have now decayed. So 1 year later, you've ended up with 500. So let's imagine I've kept hold of that substance. I don't really want to be holding this, but let's imagine I've kept hold of this substance. 1 year later, I've got 500. What happens a year after that? I'm sure you could probably guess. You'd end up with about 250 radioactive nuclei left. So I've 2 half-lives have gone by. The amount of nuclei has decreased twice, okay, 50% each time. Guess what? A year later, so 3 years after the original experiment started, I'd have about 125 radioactive nuclei left, and it's important to stress about, and we'll talk about why in a second. So every time one half-life passes, the number of radioactive nuclei decreases by 50%. Half of them disappear, hence the name half-life. Finally then, let's have a look at this. 4 years later, 62 radioactive nuclei left. Now none of this is precise, okay, 62, isn't even half of 125. And the reason that it's never going to be precise is because, as we discussed right at the start of this topic, radioactive decay is a random process. You cannot predict when it's going to happen. But half-lives are pretty accurate because it's kind of like an average, like we're counting roughly how many there are, and then over a certain amount of time we're measuring it and figuring out what its half-life is, so we can estimate that in a certain amount of time, in this case, I've made these numbers up by the way, the half-life of uranium is not 1 year, this is just for ease of use. But let's say like uranium-232, so if you had an unstable radioisotope of uranium with a mass of 232, its half-life is something like 70 years. So every 70 years, the number of radioactive nuclei decreases by 50%, but it's random. Okay, so it's never going to be precise or bang on, but we can estimate it pretty accurately. Okay, so that's what we're talking about. So let's just have a quick look at this graph then. This makes quite a nice job of it. So you can see it started off there at 100% polonium, and you can see over time the amount of polonium is decreasing while the amount of lead is increasing. So if you watch it, it actually gets slower and slower, and that kind of makes sense. Because this is exponentiality, isn't it, really? If you start off with a certain amount and it decreases by 50% each time, the first few steps look dramatic, like, oh, I've lost most of it. But then as you get down to the bottom, we're dealing with smaller and smaller numbers. Well, 50% of a small number is a small number as well. So at the bottom, it kind of flattens out quite a lot. And you can see we ended up eventually with 100% lead. Just let that run through again. So you can see every time the amount of polonium decreases, the amount of lead increases. And that's because one nuclei inside that sample of substance that you had that was unstable decayed. And as it decayed, it turned into lead. Okay, so if you're unsure why that process is happening, you need to go back and have a look at the video on nuclear equations, and I discuss the idea of one radioactive nuclei, in order to become stable, emits energy in one form or another, alpha, beta or gamma, and in doing so could change into another substance, slightly more stable. Okay, so that's it there. You can see mass of the undecayed element, and then the mass of the undecayed element goes down, as in the stuff that's left that has not yet decayed goes down over time. Okay, so that's what that's showing you. Right, there's not much else for me to tell you there, basically. Normally we do a practical if we're in a lesson, but what I want you to do is just have a quick read through this. I'll read through it actually, and then I want you to have a go at this yourself. Okay, it should be more self-explanatory as you go along. So the activity of a radioisotope can be measured using a meter. The meter records the activity of the radioisotopes in counts per second. The data collected can be used to determine the half-life of the radioisotope. This is useful because some applications require a short half-life, such as like medical tracers, whereas other applications require a use of a radioisotope with a much longer half-life, such as smoke alarms. Okay, so there's a couple of uses in there and a description of the idea that some substances have radioisotopes, I should say, have got different half-lives. Some are really, really short. You could technically have a radioisotope with a half-life of like seconds. So let's say something's got a 2-second half-life. Every 2 seconds, the amount of radioactive nuclei in that sample of substance decreases by 50%. I think uranium-238 has got a half-life of something like 4.5 billion years. So we're talking about quite a big range of half-lives here, and everything in between there as well. You don't need to worry about what affects its half-life, you just need to know what half-life is, essentially. So the activity of a radioisotope was measured every 10 minutes for an hour, and the following results were collected. Okay, so you're given a table there with some results in, you're given a pre-completed graph there, and you've got some questions. So you just need to work through those questions there, and each one's pretty self-explanatory. What I want you to do is try these yourself, pause the video, take as long as you need to fill this in, and then we'll spend some time going through it. Okay, so you're going to learn most of the stuff about half-life here from actually getting some answers from a task, kind of learning as you're doing. So yeah, pause the video. If you want to go back, go back. If you want to do some of your own research in the meantime, still not sure about what half-life is and my explanation wasn't good enough, go on YouTube, have a look, go on Bitesize, have a look, see if you can figure anything out from there. So pause the video now, and I'll come back to you in a second and we'll go through the answers. Okay, so let's go through the answers for this then. So label each axis on the graph with a quantity and a unit. Okay, so if you're going to label a graph, you first need to decide, well, what's going to go on which axis, and the thing that you change always goes on the x-axis, and in this case the thing that was changed, you can see going up in regular intervals, was the time. So we're going to stick time in minutes, because that was measured in minutes, on the x-axis. All we're left with to go on the y-axis now is count rate, and that's counts per second. Okay, so I'm going to put count rate and counts per second on the y-axis up there, and then it's just a case of slapping the numbers in. Okay, now the time in the minutes at the bottom you pretty much can't get wrong, so that's going to be going up as it's gone up there. So every increment goes up in the values that the experiment was carried out in. Common mistake is with the next bit. Okay, so people would go, all right, well, I'm going to put 700 there, and I'm going to put 520 there, and I'm going to put 400 there. Wrong. Okay, no graph should go like that. If you did that, if you just used these numbers here and slapped them straight onto your y-axis, your line would be perfectly straight every time, and this isn't going to be a straight, it's an exponential graph, which is going to be a curve. So you need to make sure that you're going up in equal, every graph you ever draw should go up in equal increments. Okay, so let's have a quick look. The way to figure that out is, what's the biggest number? 700, all right? And how many slots have I got? Well, 1, 2, 3, 4, 5, 6, 7. Well, 700 divided by 7 is 100, meaning that every one of these should be going up in 100. So that's what it should look like: 0, 100, 200, 300, so on and so forth. We can get how the rest of it works. So the first one's been done now. Label each axis on the graph with a quantity and a unit. Done. How long did it take for the count rate to fall to half of its original value? Okay, so now, I mean, this is going to be a little bit difficult for you because you've not got this in front of you. If you're in a classroom, you could do this on a piece of paper, but you're not. So you could sketch this on a little piece of paper if you've got one, or if you want to, I don't know, take a screenshot of the screen and print that off if you've got a printer, great. Or you could do it on your phone, screenshot on your phone and then annotate it on your phone, however you want to do it, I don't mind. So let's have a quick look at this. How long did it take for the count rate to fall to half its original value? Well, its original value, its starting value was 700. So every second, we was picking up 700 counts of radiation. Half of 700 is 350. So I'm going to put a little line. Excuse the inaccuracies here, you can't really get much more accurate on PowerPoint. So I've put a line at approximately 350 going across, and I go across until I hit the line, because this is the line of amount of radioactive nuclei left. So I know that it's gone from 700 to 350, half of 700. So I've gone across, I've hit the line, and then I go down. And when I go down, it's pointing to the time it would take to get to that amount of radioactive nuclei left. So that tells me it's about 25 minutes. Okay, so that the amount of time it took for the count rate to fall to half its original value is 25 minutes. What was the count rate after 50 minutes? So now we're not going across from count rate down and figuring out time. We're going up from time, hitting the line, and going across and figuring out what the count rate was. So 50 minutes. So 50 minutes is there. So you draw a line up, you hit the line, and then you go across, and that tells you that the amount of the count rate at 50 minutes was about 200. Okay, so 200 counts every second after 50 minutes. If measurements has continued to have been taken, what would be the count rate after 75 minutes? Now there's two ways you could figure this out. Okay, the first way is doing this. You could continue that line on. Again, excuse my inaccuracy there, but it's as close as I'm going to get on here. You could continue the line on, and you could add a couple more units at the bottom. So obviously these two weren't measured, but you're still going up in the same increments. So this would still leave this, make this accurate. Okay, this is called extrapolation. So we've got these many points. We can almost precisely figure out what the rest of the results could have been. So it said the count rate after 75 minutes. So after I've drawn that line in, just do exactly what I did a second ago for the question number 3. So I'll go up from 75 and I go across and I get about 110, something like that. Okay, so that's one way you could do it. The other way you could do it is to figure out what its half-life is first. So here it says what is the half-life of this radioisotope, which I'll give you the answer to in a second. But we've kind of already answered this. It says here that to go from 700 to 350 took 25 minutes. So its half-life is 25 minutes. Every 25 minutes, the amount of radioactive nuclei decreases by 50%. So if I've been asked to find out what the count rate was at 75 minutes, well, what I can do is I can take 25 minutes off that. Just do this in your head. So 25 minutes off 75 is 50, isn't it? So 50, it was about 200. So 25 minutes later, it should be half that, shouldn't it? So 25 minutes after 50 minutes, which will make 75, the amount of count rate would have decreased by 50%. So the actual answer would have been about 100. So if you did it using a line, you probably got about 110. Or maybe you've drawn more accurate than me and actually got 100. But if you calculated it in your head or on paper, however you did it, you'd have got about 100. When you get these questions in an exam, you're given a range in the answers. They'll never say, it's bang on this answer. They'll always say, oh, answers ranging between, I don't know, like 98 and 112 or something like that. So as long as you're within that scope, you'll have got the mark. Because whatever you've done to get you so close to the correct answer must have been right. Everything else must have been byproduct, maybe inaccuracy with your ruler or whatever it's going to be. What was the half-life of this radioisotope then? So if you think back to earlier on, the half-life is just how long it takes for half of all the radioactive nuclei to decay and basically turn into something else, become stable. And we did that literally right at the start, and it's 25 minutes. Because as it started off at 700 and then got to 350, that took 25 minutes to do so. Okay, and you could figure that out from anywhere else on here as well. Like if you take, it was 200 and then it went to 100, how long did that take? Well, you just look at the difference in time between 50 and 75. It's 25 minutes again. So every 25 minutes, whatever this, I don't think it told you what it was. Yeah, of a radioisotope. Every 25 minutes, the number of radioactive nuclei in this radioisotope, whatever it is, decreased by 50%. That's all half-life is. Okay, so that is that summed up. Pretty typical question this on an exam. Give you a graph, get you to do it. Sometimes they'll give you the data and just let you make the graph yourself. Yeah, that's it. Okay, so bit of an extension task here I want you to have a go at. So the task is as follows. Different radioisotopes have different half-lives. Also, they've got different uses. I want you to research 2 radioisotopes, you take your pick, I don't mind what they are, and their uses, and explain why their half-lives are important to their uses. Okay, because like I said before, you could have something with a radioisotope with a half-life of a couple of seconds, or you could have a radioisotope with a half-life of like 4.5 billion years. I personally wouldn't want to go to a hospital and have to use a radioisotope in a medical setting that had a half-life of 4.5 billion years. Okay, that does not sound appealing to me in the slightest. I want you to research why that is. Why is it important that when we use radioisotopes, we know what their half-life is, and we make sure that we use the correct half-life and radioisotope for a particular application. Okay, so you try that. It's not homework, it's an extension task because you're doing this at home already. So give that a go. If you've got any questions about that, just drop them in the Google Classroom. Whichever teachers submitted this should be able to answer them for you, or I will if I see it. And yeah, I think that's it.